In the previous video, we have seen how to create threads with MPI. MPI can take over the thread creation process and can reduce boilerplate code. However, only creating multiple threads is not particularly useful. In this video, we will demonstrate how to let the threads to communicate. We present this video by giving another toy example. Then, we let each thread to generate a random number to be added to the starting number. Then we calculate the average of the sum on each thread. Let's formalize the language a little bit. First, the main threads generate a random number as the starting number. Then, the starting number is broadcast to each rank. In the third step, each rank generates another random number and add the generated random number to the starting number. In the third step, each rank generates another random number and add the generated random number to the starting number. Finally, we aggregate the result by averaging the local sum in the main thread. Let's see how we can implement it with MPI. This is our starting point. We have the code from the previous video. I have just removed the print. Let's start by generating the random number. We define a start number and an end number variable. We also get the random number seed from the current time. A very common pattern in MPI programming is to perform different actions based on their rank index. Here, we let rank 0 serve as the head rank. We use an if clause to only generate the starting number in rank 0. Next, we need to broadcast the number to all the ranks. MPI provides a series of communication APIs. For example, here we can use the MPI bcast API to send this number to all the ranks. The first argument is the number to broadcast. It is both the sender and the receiver. The number in the sender rank will be assigned to the variable in the receiver ranks. The second and the third arguments represent how many numbers to send and what are the types of the numbers. It is very common to broadcast an array, so the count is often greater than 1. The fourth argument is the rank index of the sender rank. The last argument is the communicator. We use the word communicator to include all the ranks. Next, we calculate the local sum. This is regular C code, so nothing interesting to talk about here. At this moment, you may think all the threads are completed execution. However, on the timeline, it may actually look like this. Some threads may already have the local sum, while some other threads may not even have received the starting number. So we have to make sure that all the ranks have calculated the local sum before we can finally aggregate the data. So luckily, MPI provides a simple API called MPI barrier. It will guarantee all the threads arrive at this point before moving forward. The API is simple. It just needs a communicator as the argument, and all the ranks in the communicator will be synchronized at this point. Finally, we need to aggregate the data to calculate the final average. Since data aggregation is commonly used in high-performance computing applications, MPI provides an API called MPI reduce. It is probably the most complex API we have seen so far. It takes 7 arguments in total. But since you have seen a few MPI collective communication APIs, you may have already seen the pattern here. The first and the second argument are the source and the destination of the data respectively. So the data stored in start number variable in each rank will be aggregated to the end number variable. The third and the fourth argument are for the number of elements to process and the type of elements. Here, we're dealing with a single integer, so we pass 1 and MPI int. Next, the fifth argument is the aggregation action. Here we calculate the sum, but you can also calculate the largest, smallest, multiplication operations. You can always refer to the MPI document for a full list of supported actions. Then, the sixth argument is the root of the aggregation operation. It determines which rank will maintain the final aggregation result. Finally, we need the last argument to specify the communicator. Here we will use MPI com_world, since we want to aggregate the results from all the ranks. After the reduce operation, we print the result. So we can have a review of the process. In the beginning, we let rank 0 generate a random number before broadcasting the number to all the ranks. Then, each rank generates its own random number and synchronizes with a barrier. Finally, we aggregate the result with the reduce API. Overall, we find MPIs are very similar to GPU programming, as the threads in MPI are more likely to perform similar tasks. We will see that concepts such as barriers are also used in GPU programming. Before the end of this video, I want to show you the execution result of the program. I have added some extra prints so that you can see the process better. The starting number is 0. Rank 0 broadcasts it to all the ranks, but the number is received at different times. Process 1 already finished adding the random number, while process 2 has not received the number yet. But thanks to the barrier we have added, the final result, 58, is correct.